CPU. When you bought your laptop or phone, you probably checked exactly one chip, the processor, with the famous name on the sticker. What nobody mentions, that device carries a whole team of chips. Inside sit processors called DSP, NPU, and FPGA, quietly handling your face unlock, your noise canceling, your video calls. The famous chip you paid for isn't even doing most of the work. It's the conductor of the orchestra. The CPU has just a few powerful cores. A modern desktop chip carries 8 to 24, and each one executes billions of instructions per second. That's the entire design, a few geniuses working in a line, launching apps, running your operating system, reacting the instant you click. That's its territory. The weakness is the mirror image. Hand it 10,000 tiny jobs at once, and it slows to a crawl. Exactly why the rest of the team exists. MCU. This is the smallest computer you own, and you probably own 50 of them. A microcontroller squeezes a mini processor, memory, and storage onto one chip that costs less than a coffee. Around 30 billion of them ship every year, and they run the quiet machinery of your life. Your microwave's timer, your washing machine's cycle, every button on your TV remote. A modern car alone carries dozens. The trade-off, it's genuinely weak. Its memory is measured in kilobytes, not giga-kilo, so it will never run Windows or open a browser. It doesn't need to. It has one small job. It does it for 20 years, and it costs almost nothing. GPU. Now, take the CPU's philosophy and flip it completely. Instead of a few powerful cores, a graphics card packs in thousands of weak ones. A high-end NVIDIA card, today, carries over 16,000. Each core alone is slow. Together, they can calculate all the millions of pixels on your screen at the same instant. That's why games and 3D rendering live here. And that same talent, doing massive simple math in parallel, turned out to be exactly what artificial intelligence needs. The largest AI models are trained on tens of thousands of these cards running for months, inside data centers that cost billions to build. The catch is the appetite. A single high-end card can consume over 400 watts, more than the rest of your PC combined. Brilliant at a million things at once, terrible for your electricity bill. DSP. The real world doesn't speak in ones and zeros. This is the translator, a digital signal processor. Like the Texas Instruments chips inside headphones and phones, takes continuous signals, sound, voice, radio waves, and turns them into numbers fast enough to react in real time. Standard audio alone means measuring the sound wave 48,000 times every second. Noise-canceling headphones are the clearest demonstration. The DSP listens to the engine noise around you and instantly produces the opposite wave to erase it. If your CPU tried that, your music would stutter and your battery would die by lunch. One limit, it's a pure specialist. Signal math is its entire world. Ask it anything else, and it's lost. Quick question. How many of these chips did you know before this video? Drop the number in the comments, and if the inside of your devices is finally starting to make sense, hit the like button. It genuinely helps the channel. NPU. Because here's what happens when you shrink the GPU's AI math until it fits in your pocket. A neural processing unit is built for exactly one thing: running AI directly on your device. When your phone unlocks by recognizing your face, or blurs your background on a video call, this chip does it, quietly, on almost no power. Microsoft even made it official in 2024. A laptop only counts as an AI PC if its NPU handles at least 40 trillion operations per second. The quiet bonus is privacy. Your face, your voice, and your photos are processed on the chip. Nothing gets sent to a server. The limit is the same as its strength. AI math is all it can do. One talent, pushed to the extreme. TPU. Now take that idea and scale it up until it needs its own building. A tensor processing unit is Google's custom AI chip, and you'll never find one in a store. Google has run them in its data centers since 2015. They trained Gemini and keep services like Google Translate, answering millions at once. They are monsters. Racks of them run so hot that Google pumps liquid through the hardware to keep it alive. And the catch is built into the business model. You cannot buy one. You rent their power through Google's cloud. The chip itself never leaves the building. FPGA. Every chip so far was finished the day it left the factory. This one is never finished. A field programmable gate array is a chip whose internal wiring can be rewritten with code. An engineer can configure it as a CPU today, wipe it, and turn it into an audio processor tomorrow. The actual electrical pathways inside change. That's why companies use FPGAs, like Xilinx boards, to test new processor designs before spending millions manufacturing the permanent version. It's also why NASA put them on its Mars rovers. When your hardware is 200 million kilometers away, being able to rewire it remotely is the difference between a repair and a dead mission. The price of that freedom is speed. For any single task, an FPGA is slower and more expensive than a chip built only for that task. Which brings us to the final chip, ASIC. This is what happens when you delete the freedom entirely. An application-specific integrated circuit has its instructions physically burned into the silicon at the factory. It cannot be reprogrammed, cannot be updated, and never learns a second job. In exchange, it does its one job faster and on less power than anything else in this video. The famous example is Bitcoin mining. A modern mining ASIC makes over 200 trillion guesses per second at the puzzle that produces new coins. A speed no graphics card comes close to. But there's one fatal weakness. If that puzzle's algorithm ever changes, every chip becomes scrap metal overnight. There's no update button. The logic is fixed forever.